Now that you understood what is a signal and what is a system, next we'll see what are the different types of signals. What are the different types of signals? So the signals are mainly of three types. The first one is continuous time signal, continuous time signal, or analog signal. We also call it as analog signal. The second type is discrete time signal, and the third type is digital signal. Okay. So in general, whatever signals which you are having, they are not by nature, they are analog signals or continuous time signals. For example, I am generating a speech signal. It is a continuous time signal. Okay, it keeps on changing with respect to time, or it is also known as an analog signal. Okay, so by nature, all the signals are continuous time signals or analog signals. But nowadays we are using almost all digital devices. Okay, your mobile phone, your laptop, your TV, etc. All of them are digital devices. So if I want to give the signal to these systems, okay, your all these devices or systems, you have to give a digital signal as the input. But whatever signal which we are having which are generated by nature are all analog signals or continuous time signals. So you need to convert these continuous time signals or analog signals to digital signals. Okay, then only the digital device can perform operations on the whatever signal which I am giving as the input. So based on that, we have three types of signals. Okay, so that is continuous time signal, then discrete time signal, then digital signal. Finally, uh, digital signal is obtained. Now, let us see one by one what is a continuous time signal or analog signal. Okay, the first one, which is a continuous time signal or analog signal or analog signal. So as the name implies continuous time, the signal varies continuously with respect to time. That is, the signal is having value at any instant of time over some interval. Okay, that is, let us try to understand this graphically. Let us say I have a signal x of t. X of x is a signal which is a function of the independent variable time. So this is my time axis. Let us say my signal is varying in this fashion. Okay, so my signal is varying like this. This is what is my signal, okay, which is varying as a function of time. Okay, so here my signal, if you look at the signal at any instant of time, for example, I take this instant, so I have some signal, okay, it is having certain amplitude. Or you take at this instant, it is also having certain amplitude. The signal is existing at this instant of time. So anywhere in between these two also I have a signal. Anywhere in between these two also I have a signal. That means over certain interval, let us say I am starting from 0 to this instant of time, over certain interval, at any instant of time the signal is having certain value. Okay, so such a signal is known as continuous time signal. Okay, now why do we call it as an analog signal? Okay, sometimes the signals are analogous or proportional to certain physical phenomenon. Okay, they are analogous or proportional to certain physical phenomenon because they are varying in proportion to certain physical phenomenon, or they are varying analogous to certain physical phenomenon. We call it as a analog signal. So analog signal is another name for continuous time signal. Okay, so this is my continuous time signal. Okay, so what is a continuous time signal now? What is the definition? What is a continuous time signal? Continuous time signal is the one which has continuous time signal. It is a signal. It is a signal having value at any instant of time, at any instant of time over certain interval. Okay, it is having, so it is a signal having value at any instant of time over certain interval. Okay, so if you take this interval, it is continuous. At any instant of time, it is having certain value. So why do we call it as analog signal? The signal is varying with respect to or in proportion to certain physical phenomenon, or in analogous to some physical phenomenon. That is why you also call it as a analog signal. Okay. Now analog signal is continuous both in time as well as continuous in amplitude. That is, my amplitude is changing continuously. You can see the value of this amplitude is changing continuously. Okay, for example, if I take this as my time axis, these are the different instants of time. Okay, these are my instants of time. So as you know, the unit of time is seconds. Let us say 0, 1, 2, 3, 4, 5, 6, okay, 7, and so on. So these are my instants of time, and this is my y-axis representing the amplitude of the signal. These are the different amplitudes: 0, 1, 2, 3, 4, 5, 6, and so on. Okay. Now, if you take the time axis, it is continuous between 0 and 1. Let us say at 0.5, I have the signal. At 0.1 second, I have the signal. At 0.9 seconds, I have the signal. So, my time axis is continuous and my amplitude is also continuous. Let us say at this instant of time, I have 4. Maybe at some instant, I have 4.1. At some instant, I have 4.5. At some instant, I have 4. So, my amplitude is there. My amplitude is also having continuous values. It is not either 4 or 5 or 6. It is in between 4 and 5 also. It is having number of amplitudes like 4.1, 4.2, 4.05, 4.005, and so on. So my amplitudes are having continuous values. Okay. So my continuous time signal is continuous both in time. That is, I have 0 seconds. In between 0 and 1, I have 0.1 second, 0.5 seconds. Between 0 and 0.5, I have 0.1 seconds. Between 0 and 0.1, I have 0.05 seconds. Also, I have the signal. So my time axis is continuous, as well as my amplitude is also continuous. Okay. So that is why my continuous time signal is continuous. My continuous time signal is continuous both in time and amplitude is continuous both in time and amplitude. Okay, so this is what is a continuous time signal. Okay, this is my first type of signal. Now, what is a discrete time signal? What is a discrete time signal? Okay. So, as the name implies, the time axis is made discrete. That means I am taking the signal amplitude or the value of the signal only at a discrete instance of time. I am making the time as discrete. Okay, that means I am taking the samples of the signal, that is at zeros. Let us say I am taking the amplitude of the signal at 0 seconds, and next I am taking at 1 second, then at 2 seconds, at 3 seconds, and so on. Between 0 and 1, I am not bothered. I am not considering the signal, or I am not taking the amplitude of the signal. Between 1 and 2, I don't have any signal. Between 2 and 3, I am not taking the signal value. So I am taking the amplitude of the signal or the value of the signal only at a discrete instance of time. So that is why you call it as a discrete time signal. So I am making the time discrete. Okay. Now let us say I am taking my signal amplitude at 0 seconds. This is the amplitude of the signal. At 1 second, I am taking the amplitude of the signal. Then at 2 seconds, I am taking the amplitude of the signal. At 3 seconds, I am taking the amplitude of the signal. At 4 seconds, and so on. Okay, these are the signal amplitudes at different instants of time. So these are my samples. Okay, so taking the signal value only at discrete instants of time is known as sampling. Okay, so sampling means making the time discrete. That means taking the signal value only at discrete instance of time is known as sampling. Okay, so during sampling I am getting the samples of the signal. So this set of samples together is known as a discrete time signal. Okay, so how do we sample it? So we sample it by means of a switch. Let us say I have some electronic switch. So this is my continuous time signal. So the switch is closing at regular intervals of time, let us say NTS. Then the output signal is the sample signal, which is represented as x of NTS, where small n represents the integer. Okay, so small n is a integer here. Okay, let us say n is equal to 0, the switch is closing at 0 seconds. N is equal to 1, the switch is closing once again closing at ts seconds. N is equal to 2 ts, n is equal to 3 ts, and so on. That is, every ts seconds it is closing and it is taking the input signal, or it is taking the amplitude of the input signal. So we are generating a discrete time signal. So discrete time signal is represented as x of NTS, that is my t is replaced with the NTS. Okay, where ts is the sampling period or sampling time. So every ts seconds every ts seconds I am taking the amplitude of the signal, sampling time. Okay, so after taking the samples, whatever the set of samples which you are getting is known as discrete time signals. So these are my samples in this case here. This is my first sample, second sample, third sample, and so on. Okay, so what is ts here? Ts here is 1 second. Let us say 1 into ts, 1 into 1. This is 1 second, 2 into 1, 2 seconds, 3 into 1, 3 seconds, 4 seconds. So here in this case, my sampling time is 1 second. Okay, so it need not be 1 second always. It can be 2 seconds or 0.5 second or 0.25 seconds, so and so on. Okay, depending upon at what rate, what is my sampling rate. Okay, that is a separate topic. Okay, so at depending upon the frequency of the signal, I have to change the sampling time. Okay, high frequency signals, I should have more sample. I should have very small sampling time, or sampling rate should be high. Low frequency signals, my sampling time may be more, so I can have a lower sampling rate. Okay, so this is what is a discrete time signal. Okay, now so these values, okay, in between I don't have any signal, only these values or these samples is known as a discrete time signal. Okay, now if you observe my discrete time signal, my time is made discrete. Discrete means 0, 1, 2, 3. In between I am not taking any signal here, but the amplitude, so time is discrete, no doubt, but the amplitude is not discrete. Let us say if I take the value here, it is 4. The value here may be around some 4.5. The value here is around 3.5. The value is around 4.6. The value here is around 5.8, something on, something like that. Okay, so here the amplitudes of the signals are not taking discrete values, they are having continuous values. I don't have 4, 5, 6, but instead may have 4.5, I may have 4.6, I may have 3.5, I may have 5.8. So which are continuously changing. The amplitudes are continuously changing. So my discrete time signal, it is a discrete in time, whereas continuous in amplitude. So discrete time signal is the one which is discrete in time and continuous in amplitude. Continuous in amplitude. Okay, so it is discrete in time and continuous in amplitude. So this is what is a discrete time signal. Now let us see what is the third type of signal, that is digital signal. Okay, so I will make use of the same diagram for explaining the digital signal also. Okay, so we have seen what is continuous time, what is discrete time, then we will see what is a digital signal. Okay, now so my third type is a digital signal. So here, so once we are obtaining the digital signal, discrete time signal, okay, so once I am obtaining the discrete time signal, so I don't have signal in between here, so only these samples are taken. Okay, we are not considering signal anywhere between these instants of time. So these are my signal. This is my discrete time signal. Okay, So just I will draw an outline connecting all these points just to show you what was the original signal. Okay, this was my original signal. The dashed one is my original signal. This is the discrete time signal which I obtained after sampling. Okay. Now, if I sample it, the signal is taking continuous values. It is taking 4.5, like that. I have told you here. It is some 4.5 or 3.5 or some 5.8 and so on. I want to make the amplitude also discrete. That is, I want to take the amplitudes like 1, 2, 3, 4, 5, 6 only. I don't want to take any amplitude in between these values. Okay. So what I'm doing, I'm rounding the amplitude anywhere in between two discrete set of values to the nearest amplitude. Okay. So for example, these are my discrete set of amplitudes. Okay, these are my amplitudes, discrete values of the amplitudes which I want to round the actual amplitudes of the discrete time signal. Okay, so what I'm doing, let us say I have an amplitude which is somewhere in between 4 and 4.5. Then I'm going to round it to the nearest one, which is 4, and somewhere which is between 3.5 and 4, I will take the value as 4, and somewhere which is between 4.5 and 5, I will take the amplitude as 5. Somewhere nearer to 6, I will take the amplitude as 6. Somewhere nearer to 5, I will take the amplitude of 5. Here I will take the amplitude as 2, and this is already 2. This amplitude is taken as 2. So what I am actually doing here is, if the amplitude is anywhere between two discrete amplitude values, I am rounding it to the nearest discrete amplitude. If it is, let us say, 4.5 to 4.9, I will take it as 5. Or if it is between 4.1, 4.2 and so on up to 4.4, I will round it to 4. Okay, so rounding off the amplitudes to the nearest discrete amplitudes is known as quantization. Okay, so it is known as quantization. So what is quantization? So what is quantization? Rounding off the amplitude of the signal to the nearest discrete amplitude. Okay, so these discrete set of amplitudes they are known as quantization levels. Okay, so all these, whatever dashed lines which I have drawn here, they are known as quantization levels. Okay, and the difference between any two successive quantization levels represented as delta is known as quantization step. Quantization step, or the step size. Okay, so the step size is here is delta, in which in this case is 1. That is 6 minus 5, it is 1. Okay, so we have 1, 2, 3, 4. The difference here is the amplitude is 1. Okay, and the unit depends upon what parameter it is. If it is a volt, 1 volt is the step size. If it is milliamperes, 1 milliampere is the step size, and so on. Okay, so this is what is known as quantization. Okay, so after sampling, if you are performing quantization, whatever signal which you are getting here is discrete in time as well as discrete in amplitude. Discrete time signal is discrete in time, whereas continuous in amplitude. And now through quantization, I am making amplitude also discrete. So what is the resulting signal? The resulting signal is discrete in time and discrete in amplitude. Now, after quantization, the signal which I am getting is discrete in time and discrete in amplitude. Now, after quantization, we are doing one more operation which is known as holding. That is, we can see the samples are located at 0, 1, 2, 3, 4, and so on. In between, I don't have any signal. Now, what I am doing, I am holding the previous value. Let us say here it is 4, I am holding it up to 1. Here it is 5, I am holding the same value up to 2. Here it is 4, once again I am holding it up to 3, and so on. So this is known as holding operation. So after holding, my time is becoming continuous. You can see anywhere in between 0 and 1 I have the value. Okay, so I am making the time continuous. So after holding, my discrete in time and discrete in amplitude is becoming continuous in time and discrete in amplitude. Amplitude is remaining discrete because the amplitudes are either 2 or 4 or 5 or 6. Amplitudes are all here discrete only, but time it is made continuous. Okay, so my after holding, whatever signal which you are getting is continuous in time and discrete in amplitude. Okay, now the last step is encoding. That is, we are representing these amplitudes like 4 here, 5 here, 6 here, and so on. We are encoding. That is, we are representing the sample values. We are representing the sample values in binary form. Binary means what? Zeros and ones. Okay. So we are representing 4 in terms of ones and zeros, and so on. Then finally, we are getting the binary form. So after encoding, whatever signal which you are getting is finally known as a digital signal. Okay. So there is a separate device which is performing all these operations like sampling, quantization, holding, and encoding. So that is performed by a separate device known as analog to digital converter. Analog to digital converter. Now in ADC, how it is encoding these values, that we'll see with the help of some formula. The ADC conversion formula, so ADC conversion formula, anyhow, this is not our topic here at this point of time, but still we'll try to understand how it is going to convert into digital form or binary form with a simple example. So the ADC formula here is Vin is equal to the ADC value into V reference by 2 power n, where Vin is the voltage, here 4, 5, 6 and so on. These are the voltages which are to be converted into binary form. This is the ADC binary value, and this is the reference voltage which I am giving, and n is the number of bits. How many bits you want to use for encoding this sample values. Okay, so for example, I will, let us say, my input voltage here is 2 volts, let us say this value. Now my reference, if I take it as 4, my reference is 4 volts for example, and the number of bits which I want to use is 3. Then if Vin is equal to 2, so my ADC value into reference is 4 by 2 power 3. Okay, so 2 power 3 is 8, so ADC value into 4 by 8. Okay, 4 2s are 8, so 2 2s are 4. So what is my ADC value? Is equal to 4. 2 2s are 4. So what is 4 in binary? 1 0 0. That is if I am using 2 bits. So how you are going to encode this 2 you are encoding it as 100. Okay, so here also it is 2 once again 100. It is 2 once again 100. So in such a way you are encoding these values in terms of binary form. Okay, so these are the different types of signals. Okay, so you may have different binary values here. You can calculate according to this formula. Okay, so these are the different types of signals. So we have seen what is a continuous time signal or analog signal, and after quantization it is converted to discrete time signal. Then after holding and encoding, we are getting digital signal. Okay.